Okay, so as promised, today is going to be about something called polypols. So if you remember, yesterday I gave two lectures. The first lecture, I gave two definitions of what a positive geometry could be. Then I talked about polytopes, and we showed that polytopes in arbitrary dimension are positive geometries with linear boundaries. Yes. So today, instead, I'm going to fix the dimension. I'm going to only look at positive geometries in the plane. So x is forever going to be E2. But today, y has nonlinear components. Good. So I'm just going to start with the definition of a polypole. So the data that go into this are two polypole, are two tuples, y bullet and v bullet. Where y bullet is a tuple of at least two. So the number of, okay, this is going to be a tuple of irreducible plane curves. There are R of them, and R is at least two. I require them to be distinct, irreducible plane curves. In E2. I'm going to call these boundary curves, which in our context is clear, y. And v will be a tuple of R points. The points are called V12, V23, dot, 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 V R minus 1R, and then there is VR1. And these points are such that Vij lies on the intersection of yi and yj, but it does not lie on any of the other components. Okay, so maybe the model you should keep in mind is like a polygon in the plane, where these curves in y are the boundary lines, the edge lines of the polygon, and the Vij are the vertices of the polygon. Keep in mind. Okay, so I require that Vij lies on the intersection of yi and yj. I also want that Vij is smooth on yi and yj, and yi and yj intersect transversally at Vij. Okay, so these are called the vertices of the polypole. Okay. I'll use calligraphic P for a polypole. So if P is my polypole, then I say that it is rational. If each of the boundary curves is a rational curve. And that means that they are birational to P1. So examples of this are lines, conics, and if you want cubics, you need to have a singular cubic. Okay. Rational polypols, they will play a special role in this story. And then last bit of notation, but this is our notation from yesterday. Y is the union of all boundary curves. Okay. So notice nothing is real about this definition. So far, these curves can be anything. These points, Vij, can be anything. And even still here, these can be rational curves, but they might, have no real points. Proposition. So first result, well, or observation that maybe indicates that we are on the right track with this definition of rational polypols. If you look at the pair P2, Y, this is a pair XY in the sense of yesterday. This is genus 0. In the sense of Brown before. When all yi are rational. So in particular, a rational polypole defines a genus 0 pair. Okay, so of course, what we're gonna do is we're gonna construct positive geometries in the sense of our first definition from polypoles, and we're gonna study their canonical forms. Yes, Matteo?
So it says if you are with a non-rational, then does it fail?
That fails, yes. It is if and only if, because the genus of this will be the sum of the genera of the curves. So as soon as one is genus 1.
Okay. Is the proposition for any yi, or do they need to have intersections that like could reasonably be the vertices of the polypole?
Any yi. This is any yi. No further assumption. I will make assumptions later, but for this result, no. Anything else? Okay. All right, so we're gonna go towards canonical forms, and yesterday I already hinted at one way to find a canonical form is in the denominator you put the equation of all the boundary curves, but in the numerator you need this special thing called adjoint curve. So I'm gonna go towards defining an adjoint curve by telling you what such an adjoint should interpolate. Question is, what would be the numerator? Okay. So we're going to write RP for the residual arrangement, or early P, residual arrangement of the polypole. This is given by the singular locus of y, but subtract all the vertices. Now we're going to do examples. Okay. And the first example, and we remember from yesterday, so this is a Yes.
Sorry, a question from Zoom. Can X be birational to p squared, or must it actually be p squared?
For safety, let's say p squared today. Yeah, I mean, for statements that I'm gonna make later, this will need this. Okay, but one could ask many questions for it. Okay. Okay, this is an example of a polypol where all the boundary curves are real and they're just lines in the plane. The parameter r in this case is 5. Remember, r just counts the boundary curves. I'm gonna use a parameter n for the total degree of the boundary curves, the sum of the degrees of the yi. So that's 5 in this example as well. Okay. And the residual arrangement, maybe you remember from yesterday. So for that, I first need to tell you what are the vertices. Okay. So let's pretend that we're gonna, we want to think of this as a pentagon. So then maybe I choose let's do green for vertices, but for residual, I choose these vertices. Right, so once the lines are labeled 1, 2, 3, 4, 5, there's only one point I can choose for the vertex, right? V1, 2 is the unique intersection point of line 1 and line 2. Okay. And then the other points that you see in the picture are the residual points. This is what we did yesterday. Now, if I order the lines differently, then the vertices would be different points. Okay. So it's 5 red ones and 5 green ones. So whatever I do, this will be 5 points. Okay. This is also a rational polypol. Because lines are rational. Okay, second example. So I just said we want to step away from this linear case. We want to allow nonlinear boundaries. So now let's maybe try to think of this little curvy triangle that you barely see as our polypol. So then I choose these 3 things as its vertices. I only have 3 boundary curves, so I only get to choose 3 vertices. And all of the other points, all of the other intersection points of the conics are residual. Oh, yes. Okay.
There's going to be some notion of positive parts.
There will be.
So we're.
Yeah. So in this example, I'm gonna maybe want this to be the positive part, right? So later I'm gonna add more adjectives to the word polypol to make things more and more real. Okay. But so far we don't need that. So this is, let's do the parameters. This is a polypol with r's 3. N is, maybe someone can help me with n. 6. And a 6, and is the sum of the degrees of these conics. The residual arrangement consists of 9 points. That's true because there are no complex intersection points that we don't see. If there were, I'd have to count them. Okay. And this is still rational because conics are rational. Okay, let's go 1 degree up. So we draw an elliptic curve and a line and say, okay, I choose this as V1, 2 and this as V2, 1. How many residual points? Just the 1, right? By the way, I chose these things that everything happens again over the real numbers. So R in this case is 2, total degree is 4, residual arrangement is 1 point. And this is not a rational polynomial. Okay, smooth, plane cubic, not a rational curve. Genus 1. So how do we remedy this? Well, we make the cubic singular. Let's curve this a little bit. I keep my line. V12, V21. Unique residual point. Or is it? Okay, think about that. So R is certainly 2. N is 4. This is again rational. What are the residual points? Standing from the definition. Also the node, right? So I need this polypol has 2 points in its residual arrangement. Okay, these examples clear? Okay. Yes.
It's just like a naive question, but does the choice of the blue curves pick up like a unique positive region?
No.
No, so I could, it's definitely a choice. So
Absolutely. Yes. Absolutely, yes. More questions? So there are different ways to turn this into what I'll define as a quasi-regular polypol, which is when you choose a semi-algebraic set.
I guess it's crucial that none of these y's compare against where you can.
They're distinct. Yes.
Yes, well, I mean, I know they're distinct, but talking about the positive regions, if you use 2 curves to define 4 sides of your region,
That's not allowed. I cannot. That will we.
I mean, in the bottom in the picture there, you can the bottom right, you can define a region only with 2 curves.
Yes.
But that's not the question.
That's not a polypol. Okay. That is in fact a positive geometry,
Yeah.
but it's not a polypol. Okay. So then I'm gonna define adjoint curves from polypols. So we don't need real points for this. So adjoint curve. Okay. I need to explain one more adjective. I'm going to talk about nodal polypols. Tell you what that means in a second. So I have a polypol that is nodal, then I define an adjoint curve to be a curve that contains the residual arrangement. And it needs to have the appropriate degree. Yesterday we saw so degree of y minus d minus 1, which in our case is n minus 3. Containing the residual arrangement of the polypol. Okay, what does nodal mean? It means what you think it means. So the singular locus y only contains nodes. So this consists of only nodes. That means if you take the curve and you zoom in to a singular point, you see this. Okay, so locally it's a transverse intersection of points. These are the nodal singularities. So all my pictures are nodal polypols. Okay. So state a theorem about these adjoints. So this is a theorem from a paper that we wrote with many authors. This was in fact like a report of a reading group that we organized in 2020 and 2021. So I'll write this acronym once. It's COHN, Jene, Janestad, Rydell, Shapiro, Sind, Sorea, and you can find the full reference in my notes. Okay, so a nodal rational polypole. So all boundary curves are rational and all singularities are nodes. Has precisely one adjoint curve. Fairly unique adjoint curve. It does not contain any of the boundary curves. And again, it doesn't pass through any of the vertices. Oh. This is good news, right? Because if there's only one choice for the numerator, or at least up to scaling, there's only one choice of the numerator, then there's only one candidate for the canonical form of our polynomial. Okay, so important remark. Nodal is not necessary. It's just that if I don't assume nodal, then it is harder to say what an adjoint curve is. And I only have 1 hour. Okay, so you can adapt this definition of an adjoint curve in such a way that non-nodal rational polypoles still have a unique adjoint. But rational is. Yes, we already hinted at with the genus zero property for the in the sense of Brown-Dupont. But we can also look at my examples right here. So in this example, n minus 3 is 2. So we're looking for a conic that passes through the 5 red points. And there's only one, right? So in the plane, there are 6 conics. So when you impose 5 conditions, you expect a one-dimensional family means it's defined up to scaling. Equation is defined up to scale. Okay, so there it is. Here there are 9 points and n minus 3 is 3. So we're looking for a cubic curve that passes through 9 points. There are 10 cubics, so this again works out. I won't attempt to draw it. Okay, here n minus 3 is 1. So we're looking for a line that passes through 1 red point. Okay, now there's a pencil of solutions. Okay, so here I can draw. These are 3 adjoint lines to this polypole, but that's no contradiction because this is not a rational polypole. Okay, rational is essential. In fact, as soon as we make it rational, there is a unique line interpolating my 2 red points. Okay. Yeah, so let me write this point that I made. So the idea of why would you try to show such a result if you have a unique adjoint? the candidate. Or non-conform. All right. So here comes a definition so that we can start talking about real numbers. A quasi-regular polypol is going to be a polypol equipped with more data. I'm also going to impose that the boundary curves are real, meaning that the real points are the risk events. And all vertices are real. The extra data are as follows. First of all, I need to choose R curve segments. On each boundary curve, I can choose one curve segment. And the real points of yi, connecting v I minus 1 to vi I plus 1. Again, you could keep the example of a polygon in your mind. Right? And 2, I'm going to choose a semi-algebraic set. Which is non-calligraphic T. Such that, sorry, the semi-algebraic set is called, oh yeah, sorry. So, okay, the extra data are R curve segments and a semi-algebraic set that satisfy that our curve segments do not contain any singular points. So these curve segments are smooth on each individual yi. But I can bullet list. Each component of the interior of P is simply connected. We don't want Möbius strips. Like remember that later we're going to try to orient things. So this is one way to ensure that we can orient our manifold. And then we want that the Euclidean boundary of our semi-algebraic set is exactly the union of our curve segments. Okay. So now I think it's starting to look like what you think it's supposed to look like. So now we've chosen a way, so we've drawn our curves, we've chosen a way to go around these curves from vertex to vertex. And the curve segments we've chosen are the boundary of something. something orientable. Okay. Examples. So certainly polygons still run for competition, right? So I can draw 4 lines, call this my what were we doing? Yellow for vertices. Call these my vertices, and my boundary segments are the edges of this quadrilateral. They form the Euclidean boundary of this semi-algebraic set P. So this line segment would be one of the yi not negative. Okay, I could draw the same arrangement of lines, or something similar at least, and make a different choice of vertices. I could choose a non-convex quadrilateral by saying, okay, I order the lines differently. I say this is a vertex, then the second line is the one on the other side, then I pick this one, then this one in the back. And choose this weird thing as P. That's allowed by this definition. So notice that each of my boundary segments are smooth on the individual curves yi, but they are not smooth on the boundary curve y. So my line segments contain singularities of y, but yi non-negative does not contain any singular points of yi.
In either of these examples, could you replace P with the complement of P? Like it looks like you could use the exterior of P as your positive part.
I agree with you that it looks like that. Is that still orientable? So you need to be careful. Hold on, but that's not simply connected, right?
Why not? Or
Oh, we can go around the other side. Yeah. I think we can.
Okay.
Okay. Yeah, so I wanted to do a nonlinear example.
Later example, can we also do the quadrilateral of actually 2 triangles that kind of touch the points? Do like there's no order going to 2 lines, we've got to cut up 2 triangles.
So use this one, that one, and that one, you mean?
Yeah.
I think that's okay. Yes. But then this one would not be a vertex. So.
Right.
Yeah. I'm gonna draw something like that actually. Okay, so I wanted to do, yeah. So I need 2 lines. Okay, I could have 2 lines and 2 nodal cubics and choose these vertices. They walk like this, and you used all 4 curves, and you have surrounded this area. Okay. Good. So note that yi non-negative may contain singular points of y, but not of yi. Okay. Theorem. A quasi-regular polypol P with a semi-algebraic set P defines the positive geometry which is P2 in the sense of the first definition of yesterday. By and lamb. If P is nodal, okay, so here I really need a rational. Sorry about that. I didn't require that to be rational, but I need the boundary curves to be rational. If P is nodal, then I will write the canonical form on the other blackboard at Blackboard Management. The canonical form of this positive geometry is up to a multiple, so this alpha is just a non-zero constant times a polynomial abj divided by a product of polynomials f1, f2, fr, dx wedge dy. For some alpha non-zero, the polynomial abj, like yesterday, this is the defining equation of the unique adjoint curve, and the fi are the defining equations, the local defining equations of the yi. So here I've written the form in a chart, which is sufficiently random to seal the boundary curves. Okay. Okay. Still thinking about Lorentz examples. So I think if this other thing then would be a positive geometry, then you would want their canonical forms to add up to 0. So then the canonical form of the complement would have to be the same as the canonical form of this thing, but oriented the other way, which I think makes sense. Okay. So let's prove this. I want to at least sketch how you show this. So what we need to do is take the residues of this thing. So I hope you still remember a little bit from yesterday. So we're going to take the residue along yi of this form. Then, okay, what do we do? So we need to move the ith equation to the right. We're going to use the identity. I'm going to use the following identity. So dx wedge d fi over fi. It's the same as dx wedge, the same as partial fi partial y times dx wedge dy over fi. Okay, so I have something like this. So to write it like that, I have to divide by the partial derivative with respect to y. So this means I end up restricting the following rational function. Adjoint is in the numerator. In the denominator, I have f1 dot dot dot. I skip fi up to fr, and I have the partial derivative of fi with respect to y times dx, and this is a one form that I need to restrict to yi. Tell me if this is okay. Okay. Now, okay, how am I gonna further analyze this? In practice, I need to be able to see that the residues of this form at the vertices on yi are plus or minus 1. Okay. So now I'm going to use the fact that yi is rational. That means that there exists a normalization birational map from P1 to yi. And the geometric situation is as follows. So we have P1 with a line segment AI BI through this rational map, through this birational map. It maps maybe to a rational curve, yi. And by assumption, this line segment, so the image of this line segment is completely contained in the smooth segment of my nodal cubic. Okay. So the point AI goes here, and it will be, I will choose AI, BI such that these are my vertices. Okay, and this map by I is like it's one-to-one almost everywhere except at the singular points. Okay, so this node here has two preimages on the projective line. Draw that. This one has two preimages. So that means, so in the neighborhood of this line segment, this map is really an isomorphism. So I can calculate the residues of this form by pulling it back to P1 and just calculate the residues there. Okay. So let's do this actually. So in a local coordinate, I can write this map as follows. What did I choose? R of t divided by some denominator, s of t divided by the same denominator. And all of these polynomials, they have the degree of yi. And now I pull back my form along the map yi. So this thing, we call it, just like yesterday, we called it eta. We need to restrict this to yi. And pulling back is just a fancy word for substituting this parameterization into x and y. So what is this? It's just start by evaluating the adjoint polynomial at this parameterization. In the denominator, we get all of this. All of these fi evaluated at the parameterization times partial derivatives of the I polynomial evaluated at the parameterization. Okay, and then there is something, so here dx becomes x prime of t dt. Okay. So what x prime of t dt? You remember the chain rule. Need to get your hands a little dirty, but it's not so bad. Okay. So now it turns out, so you can think of this a little bit more. You can think of what the degrees are of the different factors. So here, if you substitute, if you plug in these formulas for phi I, you actually see that this polynomial h cancels completely. It appears with the same power in the numerator and the denominator, so you don't need to worry about that. After simplification, you just write this as follows. This is really keeping our aim in mind. We need to show that whatever we get, it has residues plus and minus 1 at these points AI and BI, right? So what we want to see is something like the canonical form of this line segment. I want to write this like this. So why do I know that these poles are here? It's because among this product, among these fj's, there is fi minus 1 and fi plus 1. And on my curve, yi minus 1 comes in here, and yi plus 1 comes in here. Right, so their defining equation will make a simple pole at ai, bi in the pullback. Okay, so I just isolate these poles because I want to keep them. And we'll be done once we show that these two things cancel each other completely. And we know that up to the scalar factor, this is the canonical form of our line segment. Okay, so let's do this. So for P and Q, by the way, are polynomials. Oh, that's okay. These are just polynomials. So to show that P is just a multiple of Q, we just need to check that they have the same roots. That's how it works for univariate polynomials. So let's see what the roots of P are. Let's just try to list them all. Let me first say that from this formula, you can count that the degree, at least the degree of P and the degree of Q are the same. And the degree is n minus 1 times ni minus 2. Right? N is as before, and ni is just the degree of y. Okay. So these polynomials have the same degree. So once we identify this number of roots, we have identified all of them. Okay, so what are the roots of P? And maybe someone has a suggestion. There's a numerator, you can look at the numerator here. Where should this have zeros? Yeah, exactly, at the residual points, certainly. So let's start with those. Okay. So the residual points come in two groups. They're all nodes by my nodal assumption. And among these nodes are the nodes of the individual curves, the nodal singularities of the individual curves, and the transverse intersections of the of different curves, okay? So the nodes of the individual curves, someone remember how many nodes does a rational curve of degree ni have? It's a mean question. And so it's ni minus 1, choose 2. The singular, so the nodal cubic has 1 singularity, the nodal quartic has 3, and so on. Okay, this is the number of nodes of yi. And now, because we're doing this pullback trick, every node counts double. Okay, so my adjoint, once we pull it back along this map, it actually has 2 nodes for each node that lies on yi. Now, the nodes that lie on the other curves, yj, we won't see them because we restrict it to yi. Okay, good. So the other residual points that we see here are the intersections of yj with yi. You sum over j not equal to I. How many points? I'll stop being equal. This just okay. So there's ni times nj, but I don't count all of them because my vertices are not in the residual points. Okay, so there are 2 vertices that are fall out of this. You evaluate all of this. You can check. This is ni times n minus 3. But then there's also this factor, which vanishes when x prime of t is 0. And this is the parameterization of our curve, right? So the derivative of the x coordinate of the parameterization of our curve vanishes when we have a vertical tangent. Okay. And this happens 2ni minus 2 times. So that's the degree of this polynomial. So naively, it looks like this has degree 2ni minus 1, but the leading terms cancel. Okay. Okay, so then if you add these 2 numbers, we are at the right degree. So these are nodes of yi. These are the intersection points with the other curves, and these are the vertical tangents. Okay, so we found all the roots of P. Now, do they coincide with the roots of Q? Yes, they do, right? Because the intersection points with the other curves are certainly in here, right? The nodes of y are certainly killed by the partial derivative of the defining equation. And this partial derivative also vanishes at vertical tangents. Okay, so also Q has these roots, so this is indeed up to a multiple. It's the canonical form of the line segment, and we know that this has the correct residues. Okay, we're not quite done, but we almost are. About can I take like 5 or 6 minutes? That's okay. So I can do this. Okay, so we have shown that the residue along yi of this form is a multiple of the canonical form of ai bi. And now the residue at ai of an iterated residue of this form is going to be plus or minus gamma. And my claim is that this does not depend on I. Okay, so once we've established that, you know, if you look at a polypol, you can go to a vertex, to this vertex in 2 different ways. Either you first take a residue here and then a residue there, or you first take a residue here and then a residue there. Okay. If all of these residues are plus minus gamma, then I can just scale the overall form by 1 over gamma to make it plus minus 1. Okay, so that's the missing step. And this is, I'm not gonna show this formally, but I hinted at this yesterday when we look locally. If you have a complete intersection, you're sort of in this situation. And yesterday we said if you first set x equal to 0, then you go to the origin, you get +1, and otherwise you get -1. That's the local calculation that shows that this is independent of I. Okay. And that concludes at least my sketch of the proof. And I wanted to end with an open problem. You can add even more adjectives to the word polypol. So if you make the additional assumption that on these boundary curve segments, there are no singular points of the big curve y. Except for the vertices, of course. Okay, so that excludes most of the examples that I drew. And in addition, the boundary curve does not intersect the interior. Then we call the polypol regular. Instead of quasi-regular, we now call it regular. Examples. Polygons are still in the running. So now our quadrilateral is still allowed, but the non-convex quadrilateral is no longer allowed. Right, I cannot do this anymore because now these points, they lie on the boundary segments, but that's not that. These are singular points of y. Convex polygons are good. Our example from yesterday, this is fine. I'm messing up the color code anyway. So so you can still take nice things like this. So the things that look like puffy or curvy polygons are still allowed. Okay. Then there's a conjecture about the zeros of the canonical form, or about the adjoint curve. This is a conjecture stated by Wachs, and I should have said much earlier that polypols were introduced by Eugene Wachs in the 70s, and his motivation was actually to study the application of shapes like this in finite element methods for solving partial differential equations. Okay, so Wachs' conjecture is the adjoint curve of a regular polypol, let's say rational regular polypol. Otherwise, it doesn't make sense to speak about the adjoint curve. The adjoint curve of a rational regular polypol does not intersect the interior of the polypol. Okay, so this is, we know this for polygons. We know this for polypols of degree up to 5. So when n goes up to 5, it's true, the conjecture. Anything else is really wide open. We don't know this for 3 ellipses in the plane. So for the little curvy triangles, okay, of course you can check in examples, but for arbitrary configuration of 3 conics in the plane, we just don't know. Right, so maybe just in conclusion, I already mentioned, so often I have talked about positive geometry of polytopes and polypols. Often in physics, we're interested in semi-algebraic sets in the Grassmannian. But these objects are also independently interesting, I think, from a mathematical point of view. And the field is still in its infancy, so lots of stuff to be done. Thank you.